Hello everyone, Mrs. Hanson here once again, continuing our lessons with Chapter 4. We've just concluded a chapter talking about ionic compounds, where a metal and a nonmetal combine by transferring electrons. We take a next step with covalently bonded compounds known as molecules, the sharing of electrons. So we'll begin with a review of the introduction to covalent bonding, where two nonmetals will combine and share a pair of electrons in what we call a single covalent bond, or if they're sharing two shared pairs, we'll know it's a double covalent bond. And yes, there isn't even a triple covalent bond. So we'll investigate what that means. We begin drawing Lewis dot structures. We had an opportunity to do so in a couple chapters back, chapter 2, for an individual atom. We said, for example, if I had a chlorine and I know that it has 7 valence electrons, I know how to represent those 7 electrons around its elemental symbol, representing its valence shell. We'll take a next step and do that for molecules and indicate how many shared pairs there are by using these solid lines to represent covalent bonds. We'll understand that the octet rule, where every atom would like to have the 8 electrons, just like a noble gas. And as with every rule, there are a few exceptions, and we'll investigate those in our third section of Chapter 4. When do we have less than 8 electrons, and when could we have more than 8 electrons around a central atom? We'll investigate the term resonance, where we have more than one correct structure for a Lewis dot representation, a resonance structure with its delocalized electrons. We'll investigate naming covalent compounds. We'll hear those prefixes mono, di, tri, tetra when we name molecules. We'll investigate molecular shapes, molecular geometry, and we'll investigate what's called the VSEPR theory, the valence shell electron pair repulsion theory. That's going to help us predict the shapes in a three-dimensional way of these molecules that we've been drawing flat on a piece of paper. We know that molecules aren't flat, that they have geometry to them, and we investigate those. And again, we'll learn VSEPR. We'll even write in our notepad that that stands for the valence shell electron pair repulsion theory. There, I spelled it right. In other words, we want to make sure that the atoms have as most space as possible when we're putting them together in a three-dimensional way. And our topic wraps up with electronegativity and bond polarity. Electronegativity measures the atom's ability to pull electrons towards itself in a shared pair. So just because 2 electrons are being shared, let's say between a hydrogen and a chlorine, doesn't mean that they're being shared equally. That sometimes the electron distribution between the shared pair is actually favoring the direction of the more electronegative element. And we'll investigate how chlorine becomes very electron rich, giving it a negative region. And we'll investigate how the hydrogen becomes very electron deficient, making it partially positive. Bonds can be polar if there is an unequal distribution of electron, and so can that be true for molecules. The entire molecule can be polar if there is an unequal distribution of electrons throughout the structure. And you have a little assigned reading towards the end of our chapter. And in your notepad, you'll notice the focus on health and medicine, and you'll investigate some covalently bonded compounds and their relationship to that field. So let's begin. We'll learn how to recognize the bond characteristics of a covalent compound, that the shared pair is very different than the last chapter's transfer of an electron. Transferring electrons in the ionic bond resulted in positively charged ions and negatively charged ions, making an electrostatic attraction, those charges being opposite and attracting each other. Well, there's no such thing as charges with a covalent compound. We're going to learn that they are actually sharing pairs and thus never a complete transfer. We'll draw Lewis structures for these covalent compounds and begin to develop an idea that these molecules have three-dimensional views, that they're not flat on a piece of paper. We'll draw resonance structures for some polyatomic ions and molecules. Molecules, those nonmetals that are bound together. 2 or more nonmetals will create a molecular compound. We'll name those and investigate those prefixes to let us know how to name binary molecular compounds. Whoops, I can spell. Binary molecular compounds. And we'll see that those molecular compounds have those prefixes in those names to just give us an idea of how many of each atom there are. The Vesper theory, valence shell, electron pair, repulsion theory will allow us to predict the molecular geometry around a central atom. And we'll be able to determine if a bond is polar or nonpolar using the strength of electronegativity, that atom's ability to pull electrons towards itself. And then finally determine if the molecule is polar or nonpolar as well. All of our learning goals shared with us on one slide. So let's begin our first section. We're introducing covalent bonds. We know that covalent bonds are the result of sharing a pair of electrons between 2 atoms that literally overlap their orbitals. When we think about shared pairs, what we're looking at is investigating those valence electrons in the outermost energy level and letting them overlap their orbitals. So we're being asked to draw a shared pair of electrons between hydrogen atoms. Notice that you would begin by simply writing an electron dot to represent the 1 valence electron from hydrogen. We know he has 1 valence electron because he lives in group 1A. I also remember that hydrogen, even though he's in group 1A, where all of the other alkali metals are, hydrogen is a non-metal through and through. That he's placed in group 1A, even though he's a non-metal, to represent his 1 valence electron. So he has 1 dot. Now, clearly, his noble gas would be, in the end of the row, would be helium. The noble gas that hydrogen would like to become would be helium's configuration of 1s2. Hydrogen is very unstable with 1 valence electron. Knowing that it could create a shell resembling a helium, that it would be isoelectronic with helium by sharing a pair of electrons, and that's exactly what it does. By combining, and combining means sharing the pair of electrons, each hydrogen now has 2 representing the configuration of helium. So let's keep in mind what I'm saying. I'm going to draw a circle around the hydrogen, and that hydrogen on the right has 2 electrons. It just happens to be sharing them with the hydrogen on the left. This right here, this overlapping area, represents a shared pair of electrons. Overlapping, probably has 2 p's. Overlapping shared pair is a single covalent bond. And when I count those for each atom, those electrons inside the circle count for both. So a shared pair between the 2 hydrogens gives each hydrogen 2 electrons to achieve the noble gas configuration of helium. So this covalent bond is 2 electrons, right? A pair of electrons in which those bonding atoms actually share 2 electrons for a single covalent bond. This is the definition of a molecule. The molecule is the biggest, discrete group of atoms held together by covalent bonds. The elemental form of hydrogen is a molecule built of 2 hydrogen atoms sharing 1 pair of electrons. So the shared pair of electrons between 2 hydrogen atoms is easy as showing a line connecting the 2 dots, a single covalent bond. Hydrogen is a diatomic molecule, just as we had listed. There are actually 7 naturally occurring diatomic molecules that we should put into our notes. Hydrogen was just one of those. And I'll redraw that. Hydrogen with its 1 valence electron combines with the second hydrogen and its 1 valence electron, forming a molecule of H2. Hydrogen is a diatomic molecule in its elemental form. It's just one of 7. Let's investigate the others. For example, let's go into the halogens and we'll see something that is very similar. Now remember, hydrogen is the nonmetal in group 1A. The halogens are those nonmetals in group 7A. So they'll have 7 valence electrons, such as fluorine. Fluorine with its 7 valence electrons. Obviously, it's very unstable with this unbonded electron, so it needs to form an octet to create stability. Notice that if it binds or bonds or combines with another fluorine in a shared pair, now each of those has 8 valence electrons. Remember how we count those? A shared pair counts in both directions. So now the fluorine has the noble gas configuration of neon with an S2P6 configuration. An 8 octet has been achieved by sharing 1 pair of electrons. So fluorine is also a diatomic molecule. Think of underneath that, you have chlorine. There's going to be a periodic trend. Chlorine with its 7 valence electrons will form a single covalent bond, forming a molecule of chlorine. Chlorine is also a diatomic molecule. And you can see that when they share a pair of electrons, each atom now has the 8 electrons it would like to have. And what happens to chlorine when it shares a pair? It becomes like argon with its S2P6 configuration, 8 valence electrons. Underneath chlorine lives bromine. Bromine also has 7 valence electrons. Are you drawing these with me? You should be. Put these into your notes. Bromine is a diatomic molecule, and so when I see its shared pair, I can now see 8 electrons around the bromine. It has now become like krypton. And krypton with its S2P6 configuration, giving bromine 8 valence electrons by sharing a pair of electrons. And one more in this group is iodine. Iodine has 7 valence electrons. It lives in group 7A. It is an unstable configuration by itself, so in nature it will help stabilize itself by just bonding to another like atom, making sure that the shared pair of electrons between the two gives its noble gas configuration, such as xenon, with its S2P6, 8 valence electrons. So 7 electrons in the halogen will share 1 pair of electrons, so each atom now has a combined number of 8 electrons. Sharing electrons allows those molecules in nature to become much more stable. We said that there were 7 naturally occurring diatomic elements. We've shown you 5 so far. Let's go to group 6A, and I'll show you the next one. Group 6A, we're going to find oxygen. Now, oxygen is a gas at room temperature, and so when we draw its 6 valence electrons, I'm just going to draw 1, 2, 3, 4, 5, 6. We can clearly see that it is unstable because it does not have its octet. Now, when I draw another oxygen, because I know it's going to be diatomic, I can see a site here where those 2 oxygen atoms can combine. And that's a first single covalent bond. But I still notice that this oxygen has a lonely electron over here, and this oxygen has a lonely electron over here. When this happens, the atoms are able to combine those electrons. Remember, they're not stationary. Our little dot symbols suggest that they're stationary, but they're not. Electrons are moving very quickly around the nucleus of an atom. So they bring them between and make a second shared pair of electrons. Now let me redraw that much cleaner. We have an oxygen with 2 lone pairs combined with another oxygen who has 2 lone pairs, and they're sharing 2 pairs, which makes this a double covalent bond. The oxygen molecule in nature is the elemental form of oxygen. We find it always combined, and in an elemental form it will be O2. It's just oxygen will have a double bond, so that when I count, oxygen and this oxygen are sharing 4 electrons. 2 pairs of electrons are being shared for a double covalent bond. And I still count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons around each of those oxygens. So oxygen is a naturally occurring diatomic molecule existing with a double bond. That's 6 of the 7. Who else? There's one more, and that's an element in group 5A. That's nitrogen. Matter of fact, I think I'm going to just give myself more room. Let me take that out, make sure I don't squish things in. Let's bring it down and give it its own space. So I'm going to talk about nitrogen next, group 5A. Nitrogen must have 5 valence electrons. We know that because it lives in group 5A. Now group 5A with its 5 valence electrons really wants to have 8, right? The octet rule. So when I redraw, I can see that I have one set of shared pair of electrons between those lone pair there. And I can see that these two can come up in the center to make a second shared pair. And I'm going to bring these guys into the center and draw a third shared pair of electrons. Think about that. If 8 is the magic number that all the atoms would like to have, nitrogen has 5 valence electrons. It's going to need 3 more, 3 shared pairs of electrons. So let's clean that up. This is too messy. This is my workspace, but this is the final answer where you see nitrogen with a triple covalent bond. 3 shared pairs of electrons. So that means 3 lines between the elemental symbols. 3 pairs of electrons being shared. And how I count that, remember a triple bond being shared gives 2, 4, 6, 8 to the nitrogen on the left, 2, 4, 6, 8 to the nitrogens on the right, and we have an octet for both atoms. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are the 7 elements in nature that exists as diatomic elements. Their elemental form is a molecule, not a single atom. There's a little sentence I use to help me remember this. A little sentence that's funny. It says, horses need oats for clear brown eyes. And of course, eyes is for iodine. Horses need oats for clear brown eyes helps me to memorize the 7 elements in nature that exist as diatomic molecules. Memorize those. All right, so we've introduced quite a bit there. We've talked about shared pairs of electrons. We've talked about single, double, and triple bonds. Let's take some next steps and catch the notes up to what we've been practicing with those diatomic molecules. A quick sip of coffee there. We have some unshared electron pairs that are called non-bonded electron pairs, or just simply lone pairs. So if I draw an example, hydrogen with its 1 valence electron, I'll draw next to it fluorine, who lives in group 7A, so I know it has 7 valence electrons. And I can see when I combine these two to make a single bond, that each has now obtained a noble gas configuration. Remember how we count that? Hydrogen, who wants to be like helium, has 2 valence electrons. So it is now like helium. And when I think about counting for this guy, it has 8 valence electrons. 8 valence electrons. Its noble gas configuration is now like neon. So each has achieved a noble gas configuration. Hydrogen, of course, only needs 2 to become its noble gas of helium. And fluorine gained 1 to become its noble gas like neon. Here's the vocabulary. we're looking at, on fluorine, 3 sets of dots that are not bonded, non-bonding pairs. And this really plays a role when we determine molecular geometry as well. The non-bonding pairs end up as dots. Not involved in bonds are non-bonding pairs. Fluorine has 3 pairs that are non-bonding. It has 1 set of bonded and 3 lone pairs. So that's how we're counting. Shared pairs involve in a bond, and the lone pairs are left as dots. Remember, hydrogen shares 2 electrons with the goal of becoming helium. Fluorine shared 1 pair with its own 3 sets of dots until it became like neon. So they want to become like the noble gas that's closest to them in the periodic table. So hydrogen is unique because of its only, it only needs 2 electrons to fill its first energy level. It has no more electrons. So if this is hydrogen, its goal is to become like helium. That first energy level is filled with 2 electrons in the S sublevel. But anything bigger than that, we know that we want to achieve the octet, just like fluorine did. By gaining 1 more electron, it became like neon, and so forth. So as we drew the hydrogen and fluorine dot structures, including all the lone pairs, that's all I did right there for you. We're looking at H combining with an F. Hydrogen has no lone pairs because it's just 1 shared pair to become helium. Fluorine with its 3 lone pairs and 1 single bond became like neon. Use the electron dot symbols to show a hydrogen atom and a chlorine atom, and we'll do this as a little example. So as we think about hydrogen living in group 1A, we know that it has 1 valence electron. And when we find chlorine, we see that it is in group 7A, so we know it has 7 valence electrons. So I see hydrogen with its 1 dot, and I see chlorine with its 7 dots. And see how I'm going to just make sure that I put the lone empty partner here next to the hydrogen. And to show a shared pair of electrons, I'm just going to connect those dots, and that represents a single covalent bond. This is a diatomic molecule because it's built of 2 atoms, but they're just different atoms. They're heteroatoms. One's a hydrogen, one is a chlorine. So HCl has 1 single bond, S-I-N-G-L-E, single bond. And on the chlorine, we see 3 lone pairs of electrons as well. Counting, chlorine now has 8 valence electrons. Hydrogen has 2 valence electrons. Hydrogen has become like helium in its count, and chlorine has become like argon with its count, the noble gas configurations of noble gases. When we begin drawing these, we've been practicing what are called Lewis structures. These are electron dot structures for molecules. So we can make dot structures for atoms, and we can combine atoms to make molecules and represent their bonding using a Lewis structure. And the goal here as we begin drawing Lewis dot structures is to satisfy the octet rule for all of the atoms, except hydrogen, who only needs 2 to be a satisfied noble gas. And we're going to go through some examples and kind of just share what they look like and start building some in a logical order. So here we have a molecule that I wanted to draw called methane. When we think about making a molecule and showing it in a Lewis dot structure, we always build around a central atom. And we're going to practice these steps over and over and over, but let me just say we want to select a central atom. And when I mean that, it's going to be in the center and all of the other atoms combine back to it. We're going to learn when we select a central atom to pick the least electronegative element, which is the same as saying pick the one that's farthest from fluorine, but never pick hydrogen because hydrogen only forms one bond, and then you're stuck with just one bond. So hydrogen is never a good choice for the center. We'll also learn that halogens are never a good choice for the center because they also only form one bond. So when I place carbon in the center of a molecule of carbon and 4 H's, the goal is to see these molecules as symmetrical. Now notice, and let me just back that up. Carbon has 4 valence electrons. It lives in group 4A. All right, so I can see what I'm coming up with the 4 dots. Since carbon lives in group 4A, 4 valence electrons, and I get a visual right away that there's 4 spots open for bonding, right? Those lonely electrons around the carbon are seeking another electron. And we know that hydrogen, with its group 1A, has 1 valence electron. And so I can satisfy hydrogen by connecting to each of these lone pairs and creating single bonds in all directions. This is a molecule known as methane, CH4, the simplest hydrocarbon in organic chemistry. Now remember, semester 2, there's a lot of organic chemistry where we investigate carbon chains. I also want us to just take a moment and notice the way that I drew this in this Lewis structure. I might be fooled into thinking this is a flat molecule on a piece of paper with a 90-degree bond angle. It is not. If you build this molecule with your molecular model kit, you would notice that it's not a 90-degree bond, that it's not lying flat on a plane, but it actually has a 3-dimensional shape to it. And that's what we can get an idea of here. Here's our carbon atom coming straight out of the page there. With leading up is a hydrogen, going behind the page, coming out of the page, going behind the page. That those atoms themselves are not looking like a right angle. So we're going to learn that to represent this, I can place a carbon attached to a hydrogen in the same plane, attached to hydrogen in the same plane, and we'll see like this wedge coming out of the plane and a dash going behind the plane. Think of that as a piece of paper, if you will. That's going to be the representation of the true molecular geometry of this particular molecule when we get that far. That the bond angles we'll learn are actually 109 degrees, 109.5 degrees in a tetrahedral shape. That's our direction of our chapter, is to realize Lewis dot structures are great for showing us connectivity, but it's not necessarily great at showing us molecular geometry. And that's kind of being both challenges in our chapters to think, okay, I can connect them. Now what do they really look like in space? Here's another example, ammonia. Of NH3. Now I'm going to select the central atom of nitrogen, and when I do so, nitrogen has 5 valence electrons. And I can see now, when I place 5 dots around the nitrogen, that it has 3 open spots for bonding. And that's exactly what happens, that the nitrogen will combine with 3 hydrogens so that everybody has an octet. When I draw the Lewis structure, I notice a lone pair on top of the nitrogen, 1 set of dots that are not involved in bonding. We'll learn how to read our VSEPR chart, that when we have the central atom leading to 3 atoms and 1 lone pair, then we're going to learn to call this trigonal pyramidal. It doesn't look like a flat object on a piece of paper. But when I build it, the ammonia molecule represents a shape in space. That the nitrogen, with its electrons up high, and leads down to, and just kind of use this spatial arrangement again, there's a hydrogen. Here, this one's coming out of the page. This one is going behind the page. That these objects have 3-dimensional shapes to them. Look at this as kind of the base of a pyramid, all sitting flat on the tabletop like a base, just like up here. These are sitting flat on the tabletop, but except this guy has something coming up high. Well, this guy has a big electron cloud up there, trigonal pyramidal. We'll learn to call tetrahedral, and trigonal pyramidal coming our way. We're just throwing out words now. And one more to investigate here. This is a water molecule. Water, of course, has oxygen in the center. Now, one of the things that we're all used to doing is combining the oxygen to hydrogen. And in doing so, we think that this looks like a very linear molecule. We might even think that this looks like a 180-degree straight line across when I look at the hydrogens coming out of the oxygen. But that is not the shape of the molecule at all. The Lewis dot shows us the connectivity, but then we have to take it a next step and think about what does it look like really as a three-dimensional object. The valence shell electron pair repulsion theory says, you know, oxygen with its two sets of dots that are not bonded, they want to be spatially as far apart from each other as possible. And we can do so by maximizing the bond angle and make this between them about 105 degrees, giving these guys as much space as possible to, kind of spread out. Those electron dots are like charges, and they want to make sure they're spread out as far apart as possible. So we will see that when this molecule of water, the oxygen has two sets of atoms it leads to, those are the hydrogens, and two lone pairs of electrons that are not bonded, we'll learn how to read our VSEPR chart and know that this is actually called a bent molecular geometry. That water is not correctly drawn as a linear molecule, but in nature it is a bent molecule, and it does so to make sure that it gives as much space as possible to these unbonded pairs of electrons. Now, I just taught you all the sections at once, but this is kind of challenging us to think, okay, step one, let's get a Lewis dot structure drawn. And then, okay, now I understand how they're connected, but what does it really look like in space? These molecules aren't flat, just laying on a paper, but they have shapes to them, and we have to investigate what they look like in space as well. So we're introducing covalent bonding, and as it's related to the periodic table. We know that they're formed when two nonmetals combine, or when a metalloid and a nonmetal combine. So thinking about nonmetal to nonmetal, we really don't have too many elements on the nonmetal side of our border. So we're just looking at how they combine to form molecules. And it begins just kind of investigating how many bonds each atom would like to have. So let's write these out together. And what we're going to do is just investigate how many bonds would it need to satisfy its octet. Alrighty, so the first one in our box there, it says hydrogen. I want us to investigate the hydrogen atom has one valence electron. So with its one valence electron, and I know that because it lives where it lives, it would like to have a noble gas configuration of helium. So I can clearly see that hydrogen would like to form one bond. And that's what I want us to just realize. How many bonds and how many lone pairs for each element? Well, hydrogen is going to want to form one bond and have no lone pairs. That's its trend to become like helium. Let's move over one and go to boron, the next nonmetal. Boron we'd call a metalloid. Boron. Now boron, who lives in group 3A, when I write its elemental symbol, we're going to see boron with 3 dots. Alrighty. With its 3 dots, how many would it like to have? How many bonds and lone pairs are likely? Well, boron with its 3 dots only has room for 3 bonds. And when I draw that out, kind of thinking about what it would look like, its 3 bonds will end up looking like an equilateral triangle when we add in the Vesper theory, the molecular geometry. 3 bonds and no dots. Well, I'll put no lone pairs. We'll learn that this is one of those exceptions to the octet rule, because it does not have 8 electrons around it. It will only have 6, and that's okay because it lives in group 3A. It only has 3 dots. It only has 3 spots for bonding. That's why we'll call it an exception to the octet rule. Let's go over to carbon next. Carbon, who lives in group 4A, we place its electron dots, 1 around each side. There's the electron dot symbol for carbon as an atom. Well, now I can see that carbon itself has 4 open spots for bonding. So when I write out how many bonds it's likely to have, it's going to have 4 bonds. And I'm kind of getting us used to the idea that they're not just 90 degrees, that these are going to have shape. But 4 bonds are going to be happening for a carbon. That's its goal, is to have 4 bonds. And of course, then it will have no lone pairs. There are no dots left. Each one is going to be connected to something else. Let's keep going. I'm going to come down here and do nitrogen. Nitrogen, who lives in group 5A. So now I can see nitrogen with its 5 valence electrons. Alrighty. Now that's a visual for us to use, that it only has 3 spots for bonding. So when I redraw and kind of think about what it would look like for drawing, for bonding, I can see 3 bonds and 1 lone pair. So that this lone pair up here plus 3 more bonds gives it the 8 electrons to obey the octet rule. Let's look at oxygen. Oxygen lives in group 6A, so it's going to have 6 valence electrons. When I think about what is it going to take to get oxygen 8 electrons, I can see that oxygen, with its 2 empty open spots there, are going to form 2 bonds and keep 2 lone pairs. When I look at fluorine next, fluorine, who lives in group 7A, we can see fluorine with its 7 valence electrons. Clearly I can see that in order to achieve an octet, the fluorine wants to form 1 bond, 1 shared pair. So we'd have 1 bond only for any of the halogens and 3 sets of lone pairs. And finally, to just wrap up that period 2, we'll look at neon. Neon, of course, is in group 8A. And so when I think of neon, does it even want to form any bonds, or is it the envy already of all of the elements up there? So there's just no empty spots open for bonding, 0 bonds, and 4 lone pairs. So we've investigated period 2, all of the non-metals, plus hydrogen really, but period 2 we did hydrogen with its 1 valence electron forming 1 bond only. Boron with 3 valence electrons had 3 bonds. Carbon with 4 valence electrons wanted 4 bonds. Nitrogen with its 5 valence electrons, 3 bonds and 1 lone pair. Oxygen then had 6 dots, 2 bonds and 2 lone pairs. The halogens would have 7 dots, so that's 1 bond to 3 lone pairs, and those halogens all follow that same trend. And then of course the noble gases, no bonding and 8 dots. That's going to help us predict how to put atoms together to form compounds, these molecular compounds that satisfy the octet We get a feel for how many dots and how many bonds each one of these atoms in the columns they represent will need. And that was the purpose of investigating how many dots, how many bonds for the elements based on their number of valence electrons. So what does this mean? Can we apply a periodic trend to determine how many bonds and how many lone pairs are predicted for these examples? I want you to find the group number they live in and represent their Lewis dot. So for example, when you find silicon, its elemental symbol Si, do you see it right below carbon? Which means it's in group 4A. So if I were to draw silicon, it's going to resemble our example of carbon, isn't it? With 4 valence electrons, I can see that it will have room to form 4 bonds and have no lone pairs. Here's bromine. Bromine has the elemental symbol Br. Do you see how it's in group 7A? It's part of the halogens. So when I draw bromine's electron dot symbol, it has 7 electrons around its symbol. Clearly I can see that it would like to have 8, so that gives me 1 bond and 3 lone pairs. Let's try sulfur. Sulfur, elemental symbol S, and it lives in group 6A. It's right under the oxygen. So if I were to draw sulfur, it will have similar properties than that of oxygen. 6 dots. I can see 2 open spots for bonding, so I would predict 2 bonds and 2 lone pairs to give it the octet. And finally, phosphorus. Phosphorus is the elemental symbol P. It's in group 5A, just like nitrogen. Phosphorus with its 5 valence electrons. I can see 3 open spots for bonding. And it has 1 lone pair. So that's the challenge there, is just trying to recognize how many bonds, how many lone pairs, with the goal of getting these atoms to an octet, except for hydrogen, who only wants 2 electrons to be like helium. Let's try another application to this, filling in the lone pairs of atoms for every main group element, except hydrogen, of course, to give it an octet. I'm going to redraw these. Here's an H connected to a carbon, H, Cl. You see, what we're asking is to find how many dots would we need on anything that's missing them. Well, hydrogen lives in group 1A, so it only has 1 dot. We realized it only has 1 spot for bonding. No dots ever around hydrogen, so it's done. Carbon lives in group 4A, and so we said carbon wants to have 4 bonds, and it clearly does, so there's no dots there. However, chlorine lives in group 7A with 7 valence electrons. It had room for 1 bond. What it's missing are its dots. Attack it this way as well. Hydrogen, 1 bond. It is completely satisfied. We know hydrogen only wants to have 1 bond. The carbon, it wants to have 4 bonds, and clearly when I look out, each carbon to hydrogen here has 4 bonds, so that's good. But when I encircle the chlorine, I can see that it's missing an octet. So to finally answer that, you just need to place 3 sets of dots around the chlorine, and then everybody has the 8 electrons it needs. When I investigate hydrogen, it only needs 1 bond. Hydrogen will never get dots. So that's always off the plate. Hydrogen, never any dots. The nitrogen, who lives in group 5A, right now the nitrogen has only 3 bonds. A moment ago we said nitrogen in group 5A, it has spots for 3 bonds, but to complete its octet, it needs a set of dots up there. Now it has 8 electrons. Next door to that is oxygen. We said oxygen lives in group 6A. There's its 6 dots. It has room for 2 bonds, which I can see there, but it's missing its lone pairs. Letter C. Hydrogen, never any dots. Carbon, it has room for 4 bonds. It has them. No lone pairs on the carbon. The oxygen, we said 2 electron bonds and 2 sets of dots. So with the carbon, the oxygen needed, with letter C, I mean the carbon needed the oxygen. In letter C, the oxygen needs 2 sets of dots. And what's going on with D? Looks like hydrogens are good. Carbon has 4 bonds, but these halogens, the bromine, they'll need their set of electrons to complete the octet, knowing that bromine in group 7A had 7 valence electrons. We said halogens need 1 bond and 3 sets of dots. So complete the dots around the bromine and you'll have all of those atoms having a complete octet. Whew, we did it. You next have an opportunity here to go into your book and kind of pull out some main events. What are the 3 to 4 most important points from this assigned reading? The assigned reading section shouldn't take too long. You're going to be looking at focus on the human body. So I'm going to let you look at that. And as you come back, what I'm going to do is continue going with Lewis dot structures and kind of just keep practicing how we write Lewis dot structures in this video. How long have I been going? I'm going to choose to pause. I'll stop here, and then when ready, do your reading first, and then come on back to this lesson and pick up with your note packs when ready.